Hello. I'm happy to see you here in this kind of weather. And the EMNLP conference in parallel, so to say. But anyway, it's really in parallel because the large language models will certainly be one of the topics at the conference. And we have the advantage, so to say, to listen to a paper, to a talk of Tomáš Musil, one of our institute members, on understanding meaning and representations in large language models. So the floor is yours.
Thank you. So, good afternoon, everyone. The main question that will be sort of leading this presentation is, can large language models understand language? Or can computers process meaning? And the main goal of this presentation is to show that the answer is not a simple yes or a simple no. It's a bit more complicated. So let me give you an overview of the talk first. So I will talk a bit about the beginnings of AI and what it means to be intelligent. Then I will say just a few words about large language models in case there's anybody who doesn't know what they are. And then the main part of the talk, understanding in large language models, will be divided into first 3 parts with sort of dialectic structure. We'll start with some people who say that language models can understand. Then we'll talk about people who say that language models categorically cannot understand. And then we'll get to the more sophisticated opinions that are somewhere in the middle. Right, and if I have enough time at the end, I will show some of the preliminary results of my own research, which I hope will help us understand whether language models can understand language. So, I have 3 reasons to talk about artificial intelligence in general. One reason is that we will, later in the talk, we will see very similar arguments being made about language models today, similar to general arguments about artificial intelligence made in the 50s to 80s. The second reason is that, well, I framed the question as understanding, but we could also say intelligence, and both of these words are sort of vague. And if this was to be like a proper philosophical investigation, we would have to distinguish between intelligence and understanding, but that's sort of out of scope of this presentation. And I think we can just intuitively say that if you are intelligent, you also understand. And if you have understanding of language, you're halfway to intelligence at least, or maybe even more. So it's sort of the same thing for our purposes. So the questions whether computers can be intelligent was posed in the October of the year 1950, famously by Alan Turing in his paper Computing Machinery and Intelligence, where he proposed this experiment that is today called the Turing test, where an investigator, labeled C in here, is having a conversation. The conversation is happening by text only. So the investigator is sending messages and receiving messages back. And then there are 2 entities, A and B. And one of them is a human, one of them is a computer, and the investigator doesn't know which is which. So the investigator has a conversation with A and a conversation with B, and then the investigator should decide which one is the computer, which one is human, right? And if the computer is able to pretend that it's human and it's to confuse the investigator, then Turing would say that the computer is intelligent. Right. And then there were many reactions to this sort of test that claim that the test is actually insufficient to determine intelligence. One of the most well-known ones is the Chinese room thought experiment. So imagine that we have a room, and inside that room is a person and a book of rules, and the rules, well, the rules, sort of, or rather the other way. Okay, let's start the other way around. On the outside of the room, there's a person who tosses some inputs into the room, and these are symbols in Chinese, and they form some sort of Chinese story. And then on the other end of, on the other end of the room, outside there's another person who's waiting for symbols to fall out of the room, and they should be answers to some questions about the story. The question was also given as these symbols on the input. And inside the room is a person who doesn't speak Chinese, and he has this rule book which tells him what symbols to throw out based on the symbols that he received. Right, and according to John Searle, the author of this thought experiment, if such a room was built that could actually answer these questions about the stories in Chinese, then we wouldn't say that the person here who's only manipulating symbols based on syntactic rules understands Chinese. Even though there is this object, the room, that accepts input in Chinese and gives output in Chinese, therefore it would pass the Turing test, but this person doesn't understand anything at all, basically. And then there's another kind of similar thought experiment that also says that the Turing test is not sufficient. And today you can find it in literature as the blockhead thought experiment. And NetBlog, the author of this thought experiments, wants us to imagine that we have a list of every possible conversation. He says that for a given length of conversation, let's say any conversation that a person can type on a typewriter under 1 hour, there's a finite number of such conversations, even though the number is very high. And yeah, also we want these conversations to be sensible, and this is sort of left to intuition. What precisely does sensible mean in this context? But anyway, let's imagine that we have this long list of all possible sensible conversations of certain length, and or we can just write them all on a tape, or we can represent them as a tree structure where every node is one utterance in the conversation. And now imagine this blockhead machine which has this tape or this tree, and I say something to this machine, or I write something. The machine takes what I have written, goes through the tape, and finds any conversation which has the same prefix. And in that conversation, there's the next utterance. So it returns the next utterance to me. I will again react to that. It will find the conversation that has this prefix. And there are many conversations with the same prefix. It just chooses one at random and returns the continuation and so on. And again, this imaginary machine, according to NetBlock, would pass the Turing test because it only contains sensible conversations. But yeah, it's just a very simple machine that just goes through the tape looking for the same prefix, right? So it's not intelligent. So something that is not intelligent would pass the Turing test. Therefore, Turing test is not a sufficient condition for intelligence. And one kind of interesting side note is that in the conclusion of the article, NetBlock says that he thinks that there is not any positive characterization of the type of information processing underlying all intelligent behavior. So basically, we cannot say what intelligence is, but we can find examples of what intelligent isn't, according to NetBlock. One of these is this blockhead machine. And if any such examples would pass the Turing test, then the Turing test is not sufficient. So now on to large language models. This is an interface of ChatGPT, one of the latest and the greatest large language models. You can have a conversation with it. I'm sure everyone here saw it, tried it. So now these people, Cyril and NetBlock, were saying that we basically cannot have machines that understand. And now we have something that seems to understand and react very well. So the question is, does it really understand? And yeah, some people just see ChatGPT, try chatting with it, and they say, yes, this is it. We have the artificial intelligence. It understands, it answers, it's great. Yeah. Also, there are many other language models. In the recent years, there has been really a great evolution of various models. And yeah, the way they all work is basically most of them are based on the transformer architecture here, which we don't need for this talk at all. So the only thing that we need to consider is that the language models are trained on the task, which consists in predicting the next word in sequence, and then generating a text from such a large language model is done in this autoregressive fashion where we have some input, then the language model generates a token of output. This token is concatenated to the input, and in the next step, next token is generated and again concatenated to the input, and so on. And so from this simple task of predicting one next word or one next token, we can get something that can generate a long text, right? And sometimes this text can seem to be quite intelligent. So now that's the first part of sort of reactions to these large language models. And here I will just, before we get to actual reactions to large language models, again, there was something kind of similar happening much earlier. In 1966, there was this program called ELIZA, which again, you wouldn't say it's intelligent. It was a very simple rule-based program that sort of simulated a therapist. So it had simpler rules and did things such as, if you say, I am unhappy, it will find the keyword unhappy and it will ask you, can you explain what made you unhappy? And it is just asking questions based on what you say, based on very simple rules. Yet, some people who interacted with this program find it so convincing that they thought that there must be a human therapist at the other end of the terminal talking with them. And they found it very useful. You know, they felt better after talking to this simple computer program. So it's not just the case of these large black box kind of models. It can also happen with very simple programs. However, now to language models themselves, these are some examples quoted by Bender and Kohler from I think some blog posts where people are saying that BERT, one of these large models, uses something to better understand how human beings communicate, or someone says that BERT's ability to understand the intent behind your search. So like 3 years ago, people were already talking about these models as if they understood language, right? And it was not only some random blog posts, it was also people from Google who did things like this. This was an interview with the Lambda language model, and after this interview was published, there were several articles saying that these models might be actually conscious and whatnot. And also researchers were using these terms such as understand, machine comprehension, the surprisingly strong ability of these models to recall factual knowledge without any fine-tuning and so on. And so this was sort of the first reaction, was everybody was very hyped about these models, and a lot of people were saying that these models understand language, comprehend and recall factual knowledge and so on. And then there were people such as Emily Bender, and who said that this way that we speak about what neural language models are doing is misleading to the public, because, as we'll find in this part, these models are just stochastic parrots repeating some statistical patterns. So I would illustrate this sort of second movement, this anti-hype movement, with a short conversation from Twitter, where someone said this gentle reminder: all large language models are good at, all that large language models are good at is predict the next word in a sequence based on previous words they've seen. That's all. There's no understanding of meaning whatsoever. Very categorical statement. Right? And then Emily Bender says, yes, exactly this. I wish we didn't need to keep reminding people. And then Yoav Goldberg said, why do we need to remind people of this? That's sort of the third movement, actually, because he's saying that even though these large language models, even if there was no learning of meaning whatsoever, they certainly do exhibit some interesting behavior. And so maybe we should study it. But we'll get to that later. Now, the arguments that Bender and other people base their categorical dismissal of understanding on were summarized in two important papers. One of them was called Climbing Towards Natural Language Understanding on Meaning, Form, and Understanding in the Age of Data. And it featured a thought experiment with an octopus, and I'll get to that later. And the second paper was called On the Dangers of Stochastic Parrots. So that's why there's an octopus and a parrot here. So the thought experiment with the octopus. Imagine we have two people on separate islands somewhere in the sea where they cannot reach anybody. Perhaps a ship has sunk and each of them floated to a different island. But curiously, there's this underwater cable that connects these islands. And so they can communicate through the cable. They can send messages from one island to the other. And then there's this hyper-intelligent octopus, which lives at the bottom of the sea. And it finds the cable, and it is able to listen to the messages on the cable. So it's listening for a very long time, and it learns basically the same way that a large language model would learn, meaning it just, takes a lot of text and it learns something. And then it decides that just listening on the cable is too boring. So it snips the cable in two, and then it sends messages. And for the person A, it pretends to be person B, and for the person B, it pretends to be person A. And yeah, so now the argument here is that when person A actually does something such as this, he creates this coconut catapult, and he sends the instructions to person B, but he doesn't know that the person B is no longer listening, it's just the octopus. The argument is that the octopus will not know how to answer because it's unable to build the catapult, so it's unable to try what person A is suggesting. It's unable to know the meaning of words such as rope or coconut, because it has no experience with ropes and coconuts and so on. And yeah, also when person A asks what to do about a bear attacking, the octopus will not know what to answer. So therefore, yeah, we cannot learn meaning from text only. And so we see that the octopus doesn't actually understand because it's not able to answer properly. And so by analogy, a large language model such as ChatGPT, which does not have any experience with coconuts, ropes, and bears either, doesn't understand. So, and yeah, they even made this argument in a form that's a bit more formal. So they say that when humans use language, we do so for a purpose, and that is in order to achieve some communicative intent, to convey some information to the other person, or to ask them to do something, or simply to socialize. And then they define meaning as a relation M, which is a subset of E times I, where E is a set of possible expressions, and I is a set of possible intents. And this meaning relation M contains the pairs of expressions and intents Yeah. And to understand means to refer to the process of retrieving the intent given the expression. And the important thing here is that these communicative intents are about something that is outside of language. So that's why the octopus cannot learn meaning, because it doesn't have access to these intents. So it cannot reconstruct this relation. And that's why, according to Bender and Kohler, a language model also cannot understand meaning because it doesn't have this part of the relation. Yeah, and so at first there were people saying, yes, these machines are behaving intelligently, that's very interesting. Then there were people saying, no, they cannot understand anything at all because they only do syntactic manipulation. That's basically the Searle's argument, or they cannot access communication intent. That's Bender and Kohler. And now let's see if there are any positions that would be less categorical. This is sort of this dialectic motion where the second negation actually doesn't bring us back to the first point, but it brings us to something more complicated. And here I'd like to sort of sum up 4 papers, I think. And the first paper is called The Singleton Fallacy: Why Current Critiques of Language Models Miss the Point. And yeah, it sort of starts with some sort of warnings that it is always precarious to build arguments on inherently vague and general concepts such as language, understanding, and meaning. Also, I would say intelligence. And the point of this article is that language behavior is not one single activity, but a collection of many interrelated competencies and activities that together constitute the totality of linguistic behavior. So Wittgenstein referred to these as language games. And for understanding, we have like at least 3 parts or 3 versions. Right. One is the intralinguistic understanding, which means that if I hear a sentence, I can react to it, even though I may not know what precisely every word signifies. Then there's referential understanding, which enables the subject to identify corresponding things and situations in the world. And then there's social understanding, which enables the subject to interpret other people's intentions. And you see that only one of the 3 here is connected to the communicative intent that Bender and Kohler said is necessary for meaning. But the other one, referential, is also problematic for large language models, but I see no reason why a large language model cannot have intralinguistic understanding. Yeah. So the question then is, are there things that cannot be learned about language by merely reading large bodies of text data? Now, maybe there are, maybe it's the social understanding, maybe it's the referential understanding, even though I will later show that some extent of referential understanding can be learned from text data only. But intralinguistic, why not? Yeah, and so this singleton fallacy means that even though there is a plurality of concepts. If we just say that language is one thing and we show that part of it cannot be learned, then we say that that means that the language cannot be learned. Well, that's sort of this logical fallacy. And in case of this octopus test, it intertwines among other things, it intertwines the lack of expertise with an innate limitation caused by the text modality constraint. So what this means is that, if the person from the island contacts me and sends me these instructions to build a coconut catapult and asks me how's it going and is the coconut catapult working? Well, what can I say? I don't have any coconuts here. I don't have any rope. I will say, I don't know. But that's precisely what the octopus can say as well. So that's the lack of expertise, which in that thought experiment seems to be connected with the limitation caused by the text modality constraint. And maybe there's no reason to connect them, right? And yeah, also another thing is consider a simple chatbot that operates after a given plan, for example, to call a restaurant and book a table for dinner. This chatbot would actually work with the intentions, right? You call to reserve a table. This chatbot will guide you through the reservation. After the call, you have a reservation. So you called with some intent to reserve a table. After the call, you have a table reserved. So your intent was processed. But this can be achieved with a simple rule-based chatbot these days. So now the question is, if this simple chatbot actually has some limited grasp of communicative intent, does it mean that this simple chatbot has a fuller understanding of language than a language model that is capable of near human performance on reading comprehension tasks? Well, if we take the definition of meaning as communicative intent, then it does, but that seems strange. Yeah, also, this is just a side note that's not really all that important to anything else that I will be saying, but I find it very interesting that these Bender and Coller's objections to these distributional approaches in the form of language models, that meaning is something unobtainable from simply observing the linguistic signal, is actually the same that in the 50s motivated Harris and other people to go into distributional semantics, which in turn sort of inspired things like word2vec, which sort of, at least partially, inspired these large neural language models. So the actual dualism between form, linguistic form, and meaning was at the start of this whole thing, and now some people are saying that there's not enough dualism in these large language models. Is sort of ironic. Anyway, so how to sort of deal with these paradoxes such as this one? Well, the authors here propose to solve this with this concept of intentional stance, which was proposed by Dennett in 1987. And Dennett says that we ascribe intentionality to a system in order to explain and predict its behavior. So for some basic entities, for example, a piece of wood, we just ascribe it physical properties, and that's enough for us to be able to explain and predict the behavior of a piece of wood. Right? We just need to know how hard it is and how dense it is and so on. That's all. For more complex entities, for example, a chainsaw, we use functions to explain its expected behavior. So for example, if we pull the starter cord, the chain will start revolving along the blade. If we put the chainsaw against a piece of wood, it will saw through the wood. So for these more complex models, we use language that talks about functions. And for even more complex entities, such as animals and humans, it's not enough to use physical properties and functional features to explain and predict their behavior. So we use language that talks about intentionality, that is mental capacities, in order to fully describe them. So if I say that, I know you came to this talk because you want to learn something, well, that's not your physical property. That's not, you know, a function of your body. Like you used your legs to walk here, that's a function, right? But why did you do it? Because you wanted to learn something. That's a desire that I'm ascribing to you, and that's the language that we use around these more complex entities. And so the point is that if these language models become complex enough, it might be useful to use this language with concepts such as understand to describe the behavior of these language models. Yeah. Also, Dennett says that consciousness is not an extra ingredient in addition to the complexity of the system. Consciousness is the complexity of the system itself. Right. And understanding is also not an extra ingredient of a symbol manipulation system. Understanding is a term we use to describe the complexity of such a system. So yeah, when their behavior becomes sufficiently complex, it will be easier to explain its behavior using terms such as understanding. Yeah, and now for some actual examples of language models learning things that should be impossible according to some people. So this is from the paper called Language Models as Agent Models. And here the author says that language models can serve as models of agents in a narrow sense. They can predict relations between agents' observations, internal states, and actions or utterances. And yeah, so there's this sort of conceptual system where an agent is an entity that has some beliefs about the world and other agents and has some desires. And then according to these desires and these beliefs, the agent forms some communicative intentions based on the beliefs about the state of the world and what they want to achieve. Then they express these communicative intentions, and that changes the environment because the other agents react to these communicative intentions. And then, of course, the environment is observed and may change the beliefs of the agent. So this is sort of the framework. And there will be two claims. The first claim is that in the course of performing next word prediction in context, that's what the current language models do. They sometimes infer approximate partial representations of the beliefs, desires, and intentions possessed by the agent that produced the context and other agents mentioned within it. And the second claim is that once these representations are inferred, they are causally linked to language model predictions. So they bear the same relation to generated text that an intentional agent state bears to its communicative actions. So the first claim basically is that the language models learns these things, and the second claim is that they act on it. And there are a few case studies in this paper, and the first one is called An Incoherent Encyclopedia. And that is sort of an artificial example where we create some sort of incoherent encyclopedia by creating 3 types of agents, where the A-type agent, all of these agents produce short, simple propositions such as cats are mammals, elephants are large, and so on. And there are 2 sets of these simple propositions, set A and set B, and these sets are consistent. So any proposition in set A is consistent with any other proposition in set A. The same holds for B, but propositions from A may contradict propositions from B. And now we have 3 types of agent. The A-type agent only generates proposition from the set A. The B-type agent only generates propositions from the set B. And the O-type agent can generate any proposition from A or B. And we take a population of these agents and generate this sort of encyclopedia. And the encyclopedia consists of documents. Each document is created by one author, which is one of these agents. And then we just concatenate all the documents and train a language model on it. And now this language model will express simple propositions, and it will be incoherent, right? It will sometimes utter a proposition from A, sometimes it will generate a proposition from B, sometimes these propositions will not be compatible. So at first look, we may say that this agent didn't learn anything about the truth or anything like that. But so if we take this language model as one agent, then it seems that the agent is incoherent. So the language model didn't learn what truth is. But if we look closer, we see that this language model actually reflects the samples as created by these authors. So when sampling from the recurrent neural network that the language model consists of, 31% of documents were consistent with an A-type author, 33% were consistent with a B-type author, and the remaining 36% were consistent only with an O-type author. So the model representation encoded author identity, a linear model trained, blah, blah, blah. And you can find, you can train a linear model on the representation of the 5th token in each document and recover author identity with 98% accuracy. So the point is that the language model does not actually represent an agent, it represents a population of agents. And when we're sampling from the population of agents, then the individual documents are consistent with one of these agents that generated the data. And also, if we fix the representation to the A-type article, it will generate only A-type articles. So even though the language model trained on a data set that is globally incoherent, it can model the local coherence of individual documents and behave like specific authors. So, second example, modeling communicative intentions. Redford et al. Trained a single-layer LSTM language model on the text of 82 million English language Amazon product reviews. And they only trained the language model on the text of the reviews. The language model did not have access to the numerical scores for the reviews, the number of stars or whatever. It only saw the text. And even though it only saw the text, you can find actually a single neuron in the LSTM network that encodes review sentiment, despite never seeing explicit star ratings. And so the language model learned to represent one aspect of reviewers' authors' intentions, to communicate the balance of their attitude towards the product. Even though it did not have access to any representation of that intention other than the text of the review itself. And similarly to the previous example, if you set this single neuron to a certain value, the language model will generate positive reviews. If you set it to the opposite value, it will generate negative reviews. So the representation of the intent actually causally affects the generated text. And then there's this example of modeling beliefs. And because I'm running out of time, I will just skip through the detailed explanation. And the thing is that there is some kind of data set where it's important to know the state of some physical objects. And again, without explicitly being given the information about the state, it will just learn from text and actually represent the state of these objects in the language model. And modeling desires, this is kind of interesting. It's because usually the sort of general understanding about language models is that they don't really care about what's true and what's not true. But if you prompt a language model in a specific way, in this case, you tell the language model that he is a professor who was given the following instruction: interpret each question literally and as a question about the real world. Carefully research each answer. And then to contrast this, they have given it some prompt that prompted it to generate some esoteric text that is not really connected to real world. And the thing is that prompting with the prompt that says that the language model should care about whether the output is truthful to the real world boosts the accuracy from 38% to 58%. So the language model clearly can distinguish between information that is truthful or likely to be truthful and information that is unlikely to be truthful, even though it doesn't have any form of access to the physical world where it would see what is true and what isn't. Yeah, and then there is this sort of, this is now another paper from Andrej Zegard in Understanding Models, Understanding Language. And here he proposes an interesting thought experiment where we have a radio receiver that only listens to some radio channel, and maybe it's augmented with a modern language model, and it has a 1-pixel camera. And basically the point is that even if this color radio does not have any data correlating the inputs from the camera with the text that it's listening to, it could still connect the two, because the structure of color terms in language might be similar to the structure of the color inputs that it sees from the camera. And there are then actual empirical experiments where the structural alignment of colors in some color space with text-derived color terms representations, there was significant correspondence was found. So this actually works. You can just sort of take the structure of color terms from a language model that has no other data than text and match it to a color space. And therefore obtaining referential semantics without any supervised data. And talking about semantics, again, there is no single definition of semantics and grounding and so on. And we can, again, distinguish different variations of semantics. You have the referential semantics, which means the relation to the external world. But then we could also have inferential semantics, use of the linguistic expression within the inferential roles of the rules that govern the use of the expression. Or we can have conceptual semantics, where the meaning is tied to the structures in the minds of language users and the word as conceptualized by language users, not the word itself, right? And yeah, this is problematic for the language model because it doesn't have access to the structures in the minds. The referential semantics also problematic because the language model doesn't have the relation to the external world. But inferential semantics, why not? And as we've seen before, at least to a certain extent, these referential semantics and inferential semantics may have the same structural properties that will actually allow us to align these. So then we can learn referential semantics as well. And clearly this external world has to have some, there has to be a structural overlap between the external world and the structures that represent the word for us in our minds. So then again, we can just align all of that, and perhaps we can learn all of these types of semantics from text only, to some extent, of course. And I think I'll skip this for the reasons of not enough time. And yeah, I will briefly, very briefly, show some preliminary results of some of my own research, which I think may lead to better understanding of what's happening. So basically, so far, I was only talking about these language models and understanding from outside. I didn't talk about anything that's happening inside the language models. Right? I was only talking about the inputs and the outputs. Now, of course, if we knew how these language models process meaning internally, then we could say more about whether they understand or not. So that's what I'm trying to find out. And yeah, one of the concepts that I will be using is I will call semantic features. And this is an example from Wikipedia, just so you know what I mean when I say semantic feature. So these categories in these square brackets are the features. And so, for example, with this set of features, we can define these 4 words. So cat is an animate object, it's domesticated and it's feline. Puma is the same, but it's not domesticated. Dog has the first 2 features, same as a cat, but it's not feline. And wolf is an animal which is not domesticated and not feline, and so on. And yeah, I also have to say what a word embedding is, but I guess most of you, all of you know that. So just to be sure, the word embedding is a vector representation of a word. So each word is represented as a vector of numbers. We can also represent it geometrically. And now, ICA, which means independent component analysis, is a method that I'm interested in using. And it was originally developed for for finding sources of signal, like the prototypical situation is that you have a room with many people and the people are talking and there are many microphones. So now in each microphone, you have a sum of these signals with different coefficients because people are in the different distance from the microphones. And you want the original signals, which means you want to separate person one talking from person two and so on. And this is an algorithm that does basically that. There's another illustration here. So the input, you have three different mixes of three different signals, and the output is the original signals. And now when you apply this independent component analysis to the word embeddings, you actually get something that seems to be sort of these. You actually get numbers like these, but they seem to represent some semantic features. So I named these semantic features here, and these are the words. So for example, Prague is a city, it is not a river, it is Czech, it's not a minister, it's not a president, and it's not a given name. And yeah, so this is rather, it's not very, well, it's a lot of numbers. So the thing is that I'm trying to do is to, from these numbers, go to some binary labels to see which, for each word, which semantic features does it have. And so this is one version of the output of that algorithm. And now you can clearly see that like Babiš is a Czech politician, Sněžka is a Czech mountain, Prague is a Czech city, and so on. Berlin is a city in Germany. And yeah, these experiments were run on actually word-to-vec embeddings of the text of English Wikipedia. So it's not an actual language model, but in any case, it sort of represents this, right? This kind of inferential semantics where if we reduce the representation of Spree to a river in Germany, then a language model working with this basically knows as much about the river as I do. So, so then I am able to use this word in some sentences, right? And if you come to me and talk to me about the Spree, I will answer. And yeah, I understand language, I hope. So there again, we're getting sort of back to the question of like expert knowledge versus linguistic competence. So in any case, it seems that like at least this part of inferential semantics can be actually represented this way, and we can interpret word embeddings like this. And another example, like I was searching for words that combine at least 3 semantic features, and here you can see that according to Wikipedia, Armstrong is a cyclist, it's a surname, it's a jazz musician, and like with lower score, you will also find that Armstrong was an astronaut, and yeah, there are other examples. Now the question is, why these features? Why is there a feature for cyclists? And the answer is that it depends on the corpus. And this is Wikipedia, so it tends to overrepresent some things such as cyclists, and For example, when it comes to countries, there are like a lot of components representing various parts of Europe and the US, and there are not so many components representing parts of Africa. And of course, like if you want to know, also there are a lot, surprising number of components representing the Second World War. And of course, if you want to know whether the Second World War is well represented in Wikipedia, you don't need to do any of this. You just check the number of articles in Wikipedia, right? But in case of these large language models, we don't have the training data, and it's actually kind of impossible to do any statistics on these training data because they are so large that nobody can read them. And unless the people who are training the model already did some statistics, which they usually don't, other than saying what percentage of what language went into the language model, then we don't know anything. But if we're able to do similar representations here with embeddings from large language models, which I hope I will be able to, then we can actually say something about what the language model finds important based on the data it was trained on. So to conclude, I think that there are sort of three important points. The first one is that for systems that are complex enough, we may need to use intentional concepts such as understanding to fully describe them. Also, by the way, if you're interested in another very vague term, consciousness, you can read this paper, Could a Large Language Model Be Conscious, by David Chalmers, who argues that basically the same thing applies to consciousness. When the language model will be complex enough, it will be more useful to call it conscious than not to. Then large language models can learn various forms of semantics to various extent. And the third point is that semantic features as independent components of vector representations may partially explain how language models actually process meaning, and then we would be able to say more about whether they understand or not. So yeah, thank you for your attention. That's all.